I'm sorry for what happened.
You should say that they are too much theoretical. They should do something.
Okay. WTM 4. So let's take it like this, and we will see if. So with guide, we move now to 2D waveguide, so the classical waveguide. From the slave waveguide to 3D waveguide. At that point, theoretical analysis, the analytical approach is much more difficult because you have two coordinated, not one, and everything is more complicated. So we do not study analytically this kind of waveguide. The results are very similar. We don't have the analytical expression, but the way of working is absolutely the same. Here you see some typical waveguide. This one, for example, this is silica, and so this is the substrate. This is the core of the waveguide in another material, silicon oxynitride. So it's an oxide with some nitrogen inside. And this is silica around. These are picture of real device. And so the light is guided by the core and around. And you see very clearly the interface between core and cladding. So it means that there are some defect there, that there are something is not so smooth as in optical fiber. So for this reason, you have higher losses. This is another one, is a strange waveguide that we studied years ago, and is still very, very used, this one. So this is glass, silica all around, this is glass, and this stripe that you see here is silicon nitride. These two are semiconductor, indium phosphate and silicon. So this is silica, this is the silicon core, and you have air on top. You can use air or glass. And these are another waveguide, and the shape of the waveguide really depends on the technology on which you build the waveguide. So you typically start, you will see next week, you typically start from a substrate, and then you deposit the material, then you etch away what you don't need it, and then you cover, etc. And you can have just one process, or in this case, 3 different deposition and drawing and etching and so on. There are as many waveguide shape as the fantasy of the designer. Here you see, let me say, no really conventional waveguide, but waveguide as well. So this one, for example, is similar to the previous one, so a rectangular core and the substrate, but there is a hole here, a slot. This is called a slot waveguide. This is a very, let me say, bad waveguide for the propagation of the light, but it's an extremely good waveguide for sensing. So assume that something is inserted here, a virus, a DNA, a protein, or a chemical compound, an atom or molecule, and perturb a lot the field, the optical field that is around the core, no? And so you immediately see if something went in this hole. So it's a good sensor. Also, this one is good sensor. It's very bad waveguide for propagation, but it's extremely good for sensor. They divide the core in 3 very thin fin. So this is the core, and the cladding is the air that surrounded the material, suspended in air. And you can imagine that if some gases flow through the core, it changes the characteristic of the propagation of the waveguide. That is something that you don't want if you want to do signal process for optical communication, but it's something that you want in case of sensing. And other kind of waveguide, this is a very interesting one, is a hollow waveguide. So the core is basically this empty space, and this is the cladding. you see here a sort of multi-layer that is useful to confine the light. And this is extremely interesting waveguide because imagine imagine to let some liquid go through. Huh? It's a microfluidic channel. So this part of space can be useful for guiding the fluid that you want to analyze and the light. So you have a very strong interaction between the light and the material that flow inside this pipe. So once again, interesting for sensing. And these are other waveguides that don't go through the confinement is no more total internal reflection mechanism in these two cases. This is quite interesting because it's really a low loss waveguide. You see a very strongly supermicron. This is the wavelength, 1.5 of the light. And in a wavelength, you have many of these, 5, 6, I mean, 2, 4, almost 6 of this pillar.
For the segmented waveguide, is there no any loss or something between the segments? I mean, is there no any change for the lights?
This is absolutely submicron, so you don't have to see as the light that propagates, find the obstacle, the part reflected, the part of continuum, because it's submicron. And obviously you have to design very carefully the aspect ratio of the pillar in order to avoid the problem that you say. But you see how many waveguides we have. So in general, these are the classical waveguide that we use. This is called a varied waveguide. Varied is sepolto. Varied waveguide, so rectangular or square core inside an homogeneous. This is a rectangular wave, optical fiber, square optical fiber. And a ridge usually is basically the same, but typically people use a ridge if the cover refractive index is different from the substrate refractive index. So you have two different materials, as a substrate and a cover. And this takes the name as ridge. There is some arbitrariness or confusion in use this name, but these are the most common. The ridge waveguide is something like this. So it's basically a slab waveguide, and you etch partially the core, the slab, and you get this shape. This is a very interesting one, very good characteristic, very low loss behavior. These three waveguides are realized by depositing material on the substrate and etching to define the core and cover again, and so on. Sometimes you cannot deposit the material, especially if the material is a crystal. You cannot deposit a crystal. You deposit an amorphous. The crystal is something that you build in another way. So in case you cannot deposit the material, you have to start from a substrate and build the waveguide inside the substrate. We will see this in lithium niobate when we will study the electro-optic modulator. So you start from a crystalline substrate that you build in another way, and you try to change the refractive index of this part that becomes the core of the waveguide without any other material, because if you add material, you add in an amorphous wave, not in a crystal wave. So you see how many waveguide. This is a slide with a summary of the characteristic of the mode of the guided mode that we already discussed yesterday and this morning. So we can skip. On this slide, you have the derivation of the group index. And let's continue. Okay, so till now we work with this mode because it was a slab waveguide. So the fundamental mode, the second mode, only one direction. If the waveguide is confined vertically and horizontally, obviously the shape of the mode becomes 2D, not 1D. So you have to imagine the core with the surrounding material, and this is the mode, the fundamental mode that is centered in the core. There is field outside, and this part are exponential decay of the field, while the central part can be described by roughly a cosine function. If you increase the frequency or the index contrast of the dimension, you can excite also higher order mode, and at this point you can have two variations in the horizontal plane or in the vertical plane. At this point, people started to talk about, they use two index, so it's TE0, the first one, and then T01 or T10, depending on how many oscillations you have in the different directions. It's just a way to give a name to this. But typically the shape of this is the shape of the transverse electric field. We represent always the intensity of the transverse electric field. Okay? I use the term TE mode, T solution, TM solution. This is correct for a slab waveguide. For a waveguide like this, you don't have any more T and TM, unfortunately. But you have the 6 components of the field. So if you draw, you take a mode. Okay, I lost the red, but I don't want to touch the cable. But black is fine as well. So this is the transverse, the intensity of the transverse electric field. So this is the fundamental mode. But as you see, the electric field has also a component, this is EY. You have a component also on the horizontal direction and in the direction of the propagation. And if you look at the magnetic field, there are the 3 components. So in general, a waveguide has 6 components of the field, not 3. So it's not rigorously T or TM, but hybrid. The modes are hybrid. However, the intensity of the longitudinal component, sometimes you have a very strong magnetic field and a weak electric field. So let's call it quasi-T or T. Sometimes you have a weak magnetic field, so the mode is hybrid, and we call it quasi-TM or TM. So when you read a book or you listen to a lesson or a talk or something, people talk about T and TM mode also for the waveguide. Rigorously are not T and TM, are hybrid, because you have all the components. But if one of the components is weak, they call it T and TM. And you have to keep in mind that it's quasi-T or quasi-TM. And the shape comes from the Maxwell equations. So there are the Maxwell equations that connect the shape of these modes, and typically derivative. So you have a derivative in one direction or in the other direction to move from this shape to the other shape. You will see in the you will see next week in the example with the numerical simulator that we do how a guided mode propagate. So this is the waveguide seen from the top. We shine the light here with a shape equal to the fundamental mode, and this gray area is the intensity of the mode seen from the top. So the mode you see propagate along the waveguide does not change the shape, is exactly always the same. This, for example, is the second order mode, the one with this shape. So this is the field that we put inside the waveguide, but the waveguide is leaky. So this mode is not guided, so it's radiative. However, if you are close to the cutoff, the mode does not disappear immediately, but you see propagate a little bit. Well, at this point, it's basically white here. There is no more field. But you see, it's 100 of micron to disappear. So if you put all your devices close one to each other, you can have an interaction due to this mode that are not guided. So we like to use this term leaky mode to say some mode that are not very well guided, but they go around. We will see a simulation of this.
So what do you say relation was its relation with cutoff?
This mode is guided, so is above the cutoff. This mode is below the cutoff. So in the omega beta diagram, you have the fundamental mode. Oops. The fundamental mode, the higher order mode. So we are here. So before the cutoff, but very close to. So you can have an effect like this in integrated optics. Another big chapter, and we will go through this problem several times, is the coupling between the external source of light, fiber, laser, another waveguide, etc., and the waveguide itself. So you shine the mode of this guiding structure to the waveguide. So you excite the modes of this waveguide. And as a first approximation, you can say that the efficiency of coupling is the overlap integral between the shape of the two modes. As a first approximation, you can say this. This is a complicated problem, and we will dedicate probably a couple of hours on this, how to move from an external source of light to the waveguide. Assume that this is a single mode. If you align the two structures, you probably excite only the fundamental mode and this mode propagating the waveguide. But if you have some misalignment, because you are putting together two objects, so in real life there is a misalignment, you can excite the higher order mode. So if the higher order mode is leaky, the mode is lost. You know? Assume you put a fiber here, but you do not perfectly align, but you do some misalignment, a slight misalignment. You excite immediately this mode, and this mode is lost. This is light that go around the chip and does not couple to the fundamental. So once again, we go back to the picture of the highway with the lane. No, if there is a misalignment, like in this case, you excite another lane. You put the car in another lane, and then if it is single mode, then it's lost. If it's a multi-mode, you excite the higher order mode that propagating the waveguide. So this is a very important point, and is related to the packaging. And I told you in the first week that the packaging of the device take the 70–80% of the cost of the device itself. And now there is at least in Europe, a large effort trying to don't solve, but try to find a solution, a practical solution to reduce the cost and increase the speed of packaging and testing and assembly. So at this point, we have seen a lot of things, and one can ask, which is the best waveguide? Which are the characteristics of an optical waveguide? No? Well, it depends on what you want to do, but these are at least a good list of the characteristics that you want from a waveguide. And the characteristic that you want really depends on the application that you have in mind. You remember the picture of the waveguide before. Sometimes you say, this is a very bad waveguide for an application, but very good for other applications. So it depends on. So typically we want single mode, not always. We want low losses. What does it mean, low? If you compare to an optical fiber, 0.2 dB per kilometer, the attenuation of a waveguide is huge. So if our devices are centimeter longer, you want a small attenuation in the centimeter range. But if we use silicon photonics, our devices are very small in the micrometer range, so we want a small attenuation at the micrometer. So 0.01 dB per micron, it's a very low loss. If you translate in centimeter, means 10 dB per centimeter. That is a very large attenuation. So it depends on the dimension of your device.
About single mode, what is the application which use multi-mode propagation? Because you said 90% of transmission are done in single mode.
Yes. First of all, some optical device to split the light or combine the light. The directional coupler works on this principle. This is the most important device in integrated optics. We'll see this. And the other reason is that a larger waveguide has a lower loss. So if you have just a straight waveguide to cross your chip to go from one side to the other one, maybe it's better to widen a little bit the waveguide, propagate it till the end, and then shrink, go back to the single mode, and do the back.
So when we increase the weight of the waveguide, we will propagate 2 modes.
It becomes multi-mode, yes, sure. The formula that I gave you for the cutoff for the thickness is valid also if you rotate your paper by or your screen by 90 degrees. So
Maybe this question I asked is because I was absent. But what is the goal of coupling the waveguide to the fiber before the receiver? What is the main goal? Why you are using waveguides and fibers together?
Oh, yes, sure. If you think to an optical fiber that arrive and you put the photodiode, you don't need nothing, no, just a couple of two. But assume you have a WDM system, so many channels. You have to separate the other channel. You have to put a filter to extract your mode. Or maybe you want to combine your signal with the local oscillator, the laser. Or you want to split the polarization. You want to do something. At that point, you need an optical device, a photonic device. So first of all, you have to enter in the waveguide. The most advanced photodetector, not really advanced, if you work at 10 gigabit per second, photodetector are realized in waveguide. It's a waveguide that works as a photodetector. It's not just an area that, and you have to shine the light on the area. If you work at 1 kilohertz, yes. But no one works at 1 kilohertz.
The order of magnitude of the optical fiber and waveguide is not the same.
The shape, the dimension
Yeah, not the shape, the order of magnitude. We know that the slide
of what?
of the waveguide and optical fiber.
The dimension. The dimension.
Oh.
The typical fiber, single mode fiber, is called SMF28. This is the classical single mode fiber for telecom or for any other application. Single mode fiber 28, I don't know from where it comes. The core has a diameter of roughly 10 micrometer. The dimension of the core, diameter of the core. The waveguide are the number that I showed you before.
So the coupling between the boats, this is much bigger than the waveguide. So
For this reason, we will dedicate a couple of hours to this problem, even more. So, you want a low or high polarization dependence? We discussed at this point, you want a polarization independent device, so low, or you want to keep the two well separated, so high. You want to be able to make a very tight band, so small bending radius. But you want a large mode because you want to couple to an optical fiber. You cannot achieve all this. So you have to find some trade-off, and this is the design of the waveguide for a given application. So these are the characteristics, and you put a priority in this list depending on your application. What else? I already show you this slide, but probably you are now able to understand a little bit better this slide that I show you the first week, probably the first day. Now you understand a little bit better, and we will come back on this slide later. I don't talk about this, and now I have half an hour to. Yes, I don't want to talk about this, and now I want to talk about bands. So we have analyzed the waveguide quite well. Obviously, there are a lot of things to say more, but I stop here. I tempted to say more, but I want to stop here. And next week you will see other properties. You go back to some of these characteristics, and now we move to bend waveguide. So at some point you have to change the direction, or maybe do some component that require a time bend. So a bent waveguide is just a straight waveguide that go around, or there is something else. So how to study the bent waveguide? Oops. Try to extract. Okay. Now, so a bent waveguide with the bending radius. This is seen from the top. Okay. So this is the cross section of the waveguide, and if you draw the refractive index, you get something like this. Is low in the core, is low in the cladding, high in the core, and back in the core. So this is the refractive index as a function of the high, so let's say x or y. Okay, this is the cross section of the waveguide, and this is the refractive index as a function of the radius of the position of the waveguide. So the geometry changes. Is no more a rectangular coordinate system. Is not more a Cartesian, but is a cylindrical coordinate system. Assume a constant bending radius, and so this is a cylindrical system. So I have to use the wave equation in the cylindrical coordinate. That makes everything more complex, because you don't have any more sine and cosine and exponential function, but you have Bessel and Hankel function. So your sine is complicated in the rectangular case, it is a mess in this. So it's not a good way. Well, people want to go really into detail, use this technique, but we stop immediately. So the other point is, can we change the geometry and get an equivalent straight waveguide? This is seen from the top. An equivalent waveguide. Because if we move to a rectangular coordinate system, then we can use the solution that we already know. And the answer is yes. The answer is yes if the refractive index along the plane of the bend where the waveguide is bent. I don't do the demonstration of this transformation that is called the conformal transformation. Sorry, but it's only 10 credits and there is more interesting things to see. It's possible to convert this problem into this one if we convert this refractive index into this one. So let's call it, how to call it, an E equivalent, x is nx, the original one, multiplied by 1 plus 2x divided by the bending radius. For some reason, that is behind this conformal transform. If you are interested, I'm happy to talk about this separately, and you have on the notes some explanation of how to do this conformal transform. But assume it is possible, and I guarantee that it's possible. So now, the refractive index is no more this one, but is this one. So is x is in this direction. So the refractive index now is go here. No, because at the end you don't see, so I write here. So the refractive index is no more this one, but is this one, because you have a linear function. So a bent waveguide is rigorously equivalent to a straight waveguide, but with the refractive index tilted. And the tilt of the refractive index depends on the bending radius. Obviously, if the bending radius is very, very large, the waveguide is more or less straight. This is a big number, and so the tilt is very weak. So basically, you have the same straight waveguide. Then if you started to tilt, to bend, the tighter is the bend, the more tilt is the refractive. So now we have to study this straight waveguide. The function are cosine, sine, and exponential, so we like it. The problem is this strange shape of the refractive index. But we can do that. So now, let's see, first of all, just try to imagine how the solution is, and then we try to approach more formally the problem.
The x in the formula is the height, the width. So I didn't understand what the x stands for in the formula.
Is this coordinate?
Okay, this one.
Is this coordinate? So the mode is around the core, is around here. However, you see that on one part the refractive index is lower, so we have a tighter confinement of the line. So the mode is, let's say, is like this, no? It's more confined. On this part, you find a lower index contrast. So the light tended to go a little bit more, to penetrate more. The gamma exponential is smaller. So the mode, you see, is you have a deformation of the mode that is tilted on this side. That is tilted toward the external of the bend, of the curve. And the tighter is the bend, the more tilted is the refractive index. So on this side you have a stronger confinement, on this side you have a lower confinement. So if you continue to bend, this mode continue to move on this side. But be careful to this point. This is the core, and the refractive index of the core is higher than the cladding to achieve a confinement. You see the problem? at some point you find an equivalent, it's not really an equivalent, refractive index that is higher than the core. So this part is a waveguide. So tends to attract the light toward the external part. That if we go back to our original problem, is the light that tends to abandon the waveguide and exit. And this is true also for a very weak bending radius, because, well, this one maybe will be like this, but at some point you get a higher refractive index. So if the mode has a tail that arrives to this point, this part is inside another waveguide and propagate outward. So to conclude this very intuitive explanation, a bent waveguide is lossy. A bent waveguide is leaky, even if the bending radius is very large.
Is it correct to say that this point, when refractive index of plating is equal to the refractive index of the core is upper bound of the bending our waveguide? Because up to this point we can bend and we can afford some losses, but if we bend more and the refractive index changes, so we will have huge losses, right?
No, because you always reach this condition. The tighter the bend, the more steep is this, so you find this condition closer to the mode. But this happens always. I continue with my explanation and then you will find the answer yourself. So with this in mind, let's consider our bend. Okay. We have a mode inside, so we have a beta here. Okay. The field just outside of the interface in the cladding has more or less the same beta because of the continuity of the field interface. However, in this case, as you know, the wave vector in the material is shorter, so we have a gamma, and the mode is evanescent, propagate in the direction of zeta, but does not propagate in the vertical direction. Now, a mode, to be a mode, needed to have the phase, needs to have a plane front. So the phase is equal everywhere. This means that use the space. This means that in every point here, the speed that can be written as r, this is r as axis, multiplied by the derivative of the angle with respect to the time is omega over beta, but this depends on the radius, on the position, so also beta depends on the position. So if we call beta 0, the beta inside the core, the beta along this axis is just beta inside the core multiplied by R divided by the position. Obviously, when the position is in the core, this simplify and beta is equal to beta 0. But if we move away, this becomes larger and larger and larger, and so this one becomes smaller and smaller and smaller. So if we draw here beta, we get a shorter vector. And this point, the wave vector in the material is always the same dimension because the material is always the same, and gamma reduce. At some point here, we have that beta star is equal to k and substance. So the k vector in the material. What is this? How do you call this?
Propagation.
Radiative.
It's a cutoff. Stop to be. So here is an evanescent field in this direction, while from here above you have a guided mode. So from here you started to propagate also in this direction. So if this point is very close to the core, you have a lot of intensity of the field here, and a lot of field goes away. If this point is far away, a very weak part of the tail of the mode arrived there, and so a very weak part is radiated away.
The direction of R small, I didn't realize this. The direction of R small, I can't figure it out.
The
Direction of R small, R.
Yes, it is the axis. Is the axis of the bend. This is the plane where the waveguide is bended, and this is the direction, the axis.
We would have the direction field outside, right?
The evanescent field is still here, and then started to adhere.
It's not clear for the
You have to think this beta that continues to reduce, and then at some point is equal to the k vector in the material, and from this point above is shorter. So here you have a beta and a radiative part and the wave vector. I want to show now the shape of the mold in a band.
But this guide is not in the core. This guide is in the substrate, not in the core.
No, we are outside of the core.
Outside the core.
Yes, yes, we are far away from the core.
This is not the mode of propagation. This doesn't deliver the information that I want to deliver. Not useful.
It depends on the attenuation. If the attenuation is, let's see this. Okay. So this is the intensity of the mode of a waveguide. This is the waveguide. So this is the classical mode inside the waveguide, the fundamental mode, and is a straight waveguide. The radius is infinite. So it's a straight waveguide. The phase of the mode is constant everywhere. The bend is this. The intensity is this one. Okay. And I want to show you. and this is the propagation of the mode in the straight waveguide. So the distance between two white or two black maximum or minima is the wavelength, and the light propagate. You see a lot of light here. You see an exponential decay. If you go away from the waveguide, decrease, and here there is no more. Straight waveguide. Now, let's start to bend the waveguide. It's more difficult. For example, 100 of micron. 100 of micron, we bent this waveguide. So this is the intensity of the mode. The maximum is in the core, but you see that it's a little bit asymmetric. You see that here is a little bit higher than this point. So the mode started to be squeezed against the external part. And the phase is absolutely flat, but at some point, far away from the waveguide, started to bend. This point is this one. At this point, the speed of the phase or the front of the mode cannot follow the others. So if we have a look to the 100, yes. This is the band with 100 micron, and you see here that most of the light stay in the waveguide and follow the band. But you see there is something here. Before was really blue. So it means that there are some field. And you see that here is a little bit bented. It does not go straight, but it remains behind. And if I continue to bend, close this one. Let's take 50, for example. Well, with 50 micron, it's clear the situation, no? You see outside how large it is. And you see that this point approach the waveguide. So we are moving down. I want to show you the movie of this case. It's 50. This is 50 micron. And this is evident, the effect. It's really evident. You enter from here, you get out from here, so it is useful. It's still useful. But this is not really guided mode, it's a leaky mode. Because formally you are losing some power. And some of the light that go, you see, in this direction. Take, you remember from my magnetic field courses, the gradient of the phase give you the direction of propagation of the wave. So it is clearly in this direction because it's in the maximum, orthogonal to the line of the phase. So it does not follow the band, while here the light follows the band. You see that this is perpendicular. And we can exaggerate and bend it by 10 micron. File, open, 10 micron, view, loop, start, and this is useless. You bent it too much. You enter from here, you see that the maximum here is no more in the waveguide, is really here. Something follow the waveguide, some power arrive at the end, but most of the light goes straight. The light travel very fast and don't like a tight band. like everyone. So this is the. So be careful to do too much tight bend in your chip because you say, okay, I lose some power because I bent the waveguide, no problem, I can amplify. But as soon as you have here another device, you have a crosstalk between the two IHN device. Huh? The device is here, far away from this one, so you expect no crosstalk, no problem, but you lose the light from this tight band and you couple to the IHN. This is the condition of 10 micron, and the amplitude, and you see that here, well, we have a maximum really here, and outside there is a lot of field, and the problematic point, so this one almost touched the core, and this point is radiating with guide, is no more a guide. Questions?
R is the more I bend, the small r is the more I bend.
The small
The
r,
value between capital R and small r. Capital R
the
is
capital R is the bending radius.
okay.
The other one is the axis.
Because
We use it X here. You can use X if you like.
it is a trade-off. Each time we bend, the trade-off between the propagation inside the core and the propagation outside the core. The more I bend, the more it will. There will be a
The
propagation.
more you bend, the more you perturb your field, the more you lose power. Yes. So, there is much more to say on bandwidth guide, but I stop here due to the limitation of time. And you can continue next week and see the simulation.